So now for a little brief interlude, let's ease into talking about systems by looking at how signals, as I called it, enter systems. And this will be important when we come to convolution in the next week. So we just want to basically see how, when we look at this boxes and arrows view of signals and systems, we have to adjust the way that we're picturing things a little bit. So what is a system? A system is a function that maps an input signal to an output signal. So this abstracts away the sort of internal operations of the system, like what it's implemented in. Is it a system? Is it a mechanical system? Or is it an electrical system? Is it a circuit? You know, we're just looking at signal x of t comes in, a signal y of t comes out, or x of n comes in and y of n comes out. And all systems are going to be kind of equivalent to each other if they have the same input-output behavior. That is, for a given x, we always get the same y. So the question is, how can we go to characterize different system properties in terms of this input-output behavior, as we call it? So we represent systems in our block diagrams, remember, as things in boxes. So for example, we have systems like a delay, which is, y of t is just x of t minus tau is a delay of tau. We have an accumulator. An accumulator adds up the input signal from minus infinity up to time n, and that's the output at time n. It's just accumulating the signal x of k. There's a rectifier, which sort of you can think of as acting like it's a rectifier. You've seen those in a circuits class, hopefully. It just takes the absolute value of the signal. If it took only the positive part of the signal, it could be like a diode. Squaring is we can just think of that as calculating the instantaneous power. So that's another type of system. And then we've seen these upsamplers and downsamplers. Those are also types of systems that operate, for example, in discrete time. So let's look at a signal going into a system. So here I plotted a signal. It's delta of n plus 2 delta of n minus 1. So we can see it up here. Up here we can see it over here. So here's a plot of it, and it goes into the system. And at time 0, though, what you should happen is that the signal x0 should enter the system. So if I draw a plot of the signal and then say, oh, it's going into the system, it's kind of going in backwards if you think about it. So really, what I have to do is sort of flip the signal to show that if it was actually going along the wire, the part that's 0 would come first, and then the part that's at time 1 would come in next. So in fact, the picture looks like this. The signal here is flipped, and this is an important concept that's going to come up when we discuss convolution. So we'll see a little preview of this on the next page. But the important thing to notice is if I had a signal, suppose we can think about one in continuous time. So suppose, here is my signal in continuous time, then what I'm going to have to do is flip it. Now let's see if I can do this. At time 0, it looks like it's coming in like this instead. So let's see if I can. I know I'm not the greatest at drawing, but here, this part here is the same as this part here. So when I plot the signal, I plot it at time equals 0, but here I'm plotting it. It basically starts at going in backwards. If I progress along the signal, I'm drawing it out. Like this, and then drawing it out like this as it's going into the system. Right, so that's how it goes in on the wire, actually. So let's see a quick example of this. So suppose y of n is 3 times x of n plus 2 times x of n minus 1 plus x of n minus 2. And we can represent this graphically as here's my original signal, right? And so I have to flip it. So remember, this is delta of n plus 2 delta of n minus 2, or n minus 1 rather. And it goes into this system. And basically you can see what happens in first is at time n equals 0, at n equals 0, we have 3 times x of 0, which is, 3 times x of 0, plus 2 times x of minus 1, plus x of minus 2. So that's just 3 times x of 0, and that's equal to 3. Right? And then at time 1, we shift over this signal gets shifted over by 1, and we go from here to here. And we can see that we're going to get 3 times x of 1 plus 2 times x of 0 plus x of minus 1. X of minus 1 and x of minus 2, for example, are both 0. So here I'm going to get 3 times 2 for the x of 1 and 2 times 1 for the x of 0. So 6 plus 2 is going to be 8. And then we can see we go from here to here, we clock it in once more, and we get 3 times x of 2 plus 2 times x of 1 plus x of 0. So here I'm just going to get the 2 times x of 1, which is 2, plus x of 0, which is 2. I'm going to get 4, and so on and so forth. Then you can go from here and you can try to calculate for yourself what happens at n equals 3. So you can see how the input signal enters and leaves the system by sliding this flipped signal into the system. We'll see how this works mathematically in the coming days. So this is just really a preview of this convolution operation that we're going to talk about later. So just keep this in the back of your mind as we go along.